Thank you. So this work was supported by Survey Leader and was done in collaboration with the Astrobiology Analytical Lab and NASA Goddard. So, first, a little bit of background. Why do we care about the survivability of amino acids on the moon? Well, many decades ago, when we brought back some samples from the lunar surface, we found organics within these samples, and this was from the Apollo era. But even in recent years, during the ANGSA reanalysis of these samples, we found organics in them still. So this is really interesting. This raises the question, did these organics really survive on the lunar surface all this time, or maybe did we somehow introduce contamination to our samples? And being able to answer this question has these broad implications about like the proliferation of prebiotic molecules throughout our solar system. And it also helps to inform us about future sample collection and handling strategies, especially since we are planning to go back to the moon. Okay, so our experiment has 3 steps to it. The first step is, well, to dose lunar simulant soil with amino acids, and we chose JSC1A for this. The second step is to expose these samples to lunar-like conditions, and all this took place in our homemade experimental setup, and looks a bit complicated, but I want to draw your eye to the glowing test tube at the bottom center of this image, and that's where all the action happens. That's where our sample is, and then everything else in this picture, so quite a few things, helps to support the action happening in this central test tube. So here's a zoomed in schematic of it. We have our doped amino acid in lunar simulant at the bottom of the test tube, and we can evacuate this, create vacuum conditions inside this test tube. We can introduce hydrogen gas, and then we can turn that hydrogen gas into plasma with a microwave cavity, and this also emits Lyman alpha UV radiation. So that's the setup. And then and then this is a cute picture of it glowing in a test tube, which I wanted to share. And then finally, after treating our sample with whatever treatment, and I'll go through that in a bit, we need to quantify the surviving amino acids within our lunar simulant soil sample. And this was done in collaboration with the Astrobiology Analytical Lab, and they use high-performance liquid chromatography mass spec. I'm really proud to be working with these guys. These are the same folks who discovered the amino acids and other organics in the Bennu sample from OSIRIS-REx. So it's a really sensitive method, and I'm so happy to be able to work with them. Okay, so some results. I'm going to go through them systematically. So each color represents a different amino acid, and they are going through different treatments of vacuum, hydrogen gas, and then UV and plasma irradiation. So each amino acid is divided into 2 samples. There's the dust sample, and then there is the wash, or the I call it wash sample. So the dust sample is pretty straightforward. After taking it out of the test tube, taking the test tube out of the experimental apparatus, we pour the dust out and we measure the surviving amino acids within these dust samples. But then we also rinse the test tube with a solvent so that any remaining amino acids stuck at the bottom of the test tube are also captured and also analyzed. And we sum these 2 up, and I'm plotting them here on the graph for you. The horizontal axis is the different treatments we have, and the vertical axis shows basically survivability. So a 1 would be 100% survivability, and a 0 means none of the amino acids survived. What we're seeing here is that when we expose our amino acids to just vacuum conditions with a low or high vacuum, which is up to about 10 to the minus 7 torr, we see a drop in survivability, but not too much difference between the levels of vacuum. Then when we introduce hydrogen gas, the survivability drops a little bit too, but not by too much compared to the vacuum. But once we turn on the plasma and the UV radiation, the survivability just plummets. It's very little, but interestingly, it's not 0. And this was interesting to us. A second interesting point that I want to bring up is that most of what survives was in the wash. It was stuck at the bottom of the test tube rather than in the layer of dust. And I want to come back to this in a little bit. But another thing we tried was just to vary the amount of radiation that our samples were exposed to. So varying from a couple of lunations worth of UV radiation all the way up to about 20 years worth of UV radiation on the moon. And as you might expect, with an increased amount of radiation, the surviving organics decreases. And once again, we're seeing that most of what survives at the bottom of the test tube rather than in a dust sample itself. Really interesting point. You can, if you want to, fit all these survivability rates to amount of radiation, and you can get slightly different decay rates for each of these amino acids. And another interesting point, and take this with a grain of salt, is when you fit this to an exponential decay curve, you can take T, time, amount of radiation to a really, really large number, and then you get the survivability rate equals to Y naught. And interestingly, for all our samples, Y naught is not 0. And this is just, well, take it with a grain of salt, but it suggests that even with indefinite time, maybe you don't get full wipeout of organics. Okay, so remember I talked about how a lot of what survives was stuck to the bottom of the test tube rather than within the dust sample. That gave us a hint that maybe there's something to do with like shielding that might be helping our amino acids survive these radiation conditions. So we decided to test it. We put our doped amino acids at various depths within a column of undoped JSE1A, and we also put in a couple of trials these doped amino acids on the surface of this column of pristine JSE1A. And for this set of trials, we managed to get our hands on some isotopically labeled amino acids, and these don't exist anywhere in nature. So that helps us be really confident that we're not really contaminating our system, and we're pretty sure of our results. So here's the data. On the horizontal axis is all the amino acids that we tested, and the vertical axis, once again, is the survivability rate of these amino acids. And if we are looking just at the non-buried amino acids, so the dark green curves, we see that the survivability rate is about 30 to 40%. But once you bury the amino acids just slightly, just a couple of millimeters, our survivability rate shoots up to like 90%. And if you keep increasing the burial depth, the survivability rate still stays really high because it's already so high. So this is super cool, and if you don't remember anything from my talk, remember this one point, which is that we are finding that amino acids can survive in lunar soil, at least on human timescales. And so when we go back to the moon and we are trying to collect samples, especially if we're looking for organics, this is something to really think about when we plan our processes and how we want to go about doing it. Okay, so we have some next steps that we're thinking about. We want to identify the breakdown products of this process. We're also looking at more complex organic molecules like peptides, maybe nucleobases, maybe if we are really lucky, we can do like bacteria, something like that. So this paper has been, it's in review at PSJ, so look out for it. And that's it. Thank you.